next one is going to be a real life example of a step function. So the cost of a long distance daytime phone call from Toronto, Canada to Mumbai, India is 69 cents for the first minute and 58 cents for each additional minute or even part of a minute. So if you go a second over, now you're going to spend more money. Draw the graph for the cost C. All right, so what we're going to do here is we first want to figure out what's going on. Okay, so we have that if we are talking for 1 minute, we're going to spend 69 cents. Really, anywhere from picking up the phone until we hit that 1 minute, it is 69 cents. So let's start to make sort of a chart. Maybe we'll do a sideways chart here. So this could be the time that we're on the phone, and then the actual cost, so C of T, cost as a function of time. So if I spend anywhere from 0 to 1 minute, I'm going to spend 69 cents. If I spend anywhere from after 1 minute, even a second passed, until, not XT, until 2 minutes, I'm going to spend an extra 59 cents. So 0.69 plus 0.59. If I talk for an additional minute, so that'll be between 2 and 3 minutes, then it'll be 0.69 plus 58 plus another 58. So really plus 2 times 0.58 and so on. And I can continue doing this. So what's going to happen is whatever the kind of starting number is here is going to be the number I'm multiplying by here. And when I go to draw this step function, which we're not going to talk negative because you're not going to talk for negative minutes, you're going to be at 69 cents from 0 to 1. If it's 0, you won't actually spend any money because that's not picking up the phone. You'll be at 69 plus 58. So let's see. 0.69 plus 0.58 is $1.27 when you are after 1 minute up until and including 2 minutes. And we'll just continue adding 58 cents. So this is 185 at 2 minutes just after, and it ends at 3 minutes. And this will just continue on. So we have two different kinds of functions when we're describing them. We can have continuous functions or we can have discrete functions. And really this is not considered a continuous function, the step function, because we have these gaps. Whereas continuous functions should have no breaks or holes in them whatsoever. Here I'm seeing I've got these kind of holes. I pick up my pencil to continue drawing. So the functions that we saw in examples 1, 2, and 3 are even, some of the other ones were continuous, but this one, sorry, these are misnumbered. But example 5 here is not continuous. Okay. Skipped over some of the graphing calculator ones. You're going to see that in tomorrow night's video. All right, the vertical line test, or you might have called it VLT just for short. You definitely saw this in Algebra 1, maybe even in middle school. If I have a graph to determine if I have a function, I draw a vertical line, or maybe I use my pencil or my finger to kind of run across the entire graph. And as long as I only am ever touching one point at most at a time, it's a function. So on the left here, this graph is a function because no matter where I draw my vertical line, I will only ever intersect the graph at one point. However, as long as I can find one spot where I intersect in more than one place, then it is not a function. So I can draw a vertical line here on this graph on the right, and I see I intersect in 2 points at the same time. So this is not going to be a function. So we're going to use that vertical line test to help us out. In example 6, I see that I have 2 intersection points here. So this is not a function. No matter where I draw a vertical line in the second one, it works, no problem. It's only ever 1 point at a time. So this is, yes, a function. Same here. This is a function. But if I draw my vertical line 1, 2, 3 points, depending on where I draw it. So that is not a function. Any question in the variables x and y defines a relationship between these variables. So for example, the equation y minus x squared is equal to 0 defines a relationship between y and x. So to find out if the equation defines y as a function of x, what we do is solve for y. We want to see, can we get y by itself and then see all of the x on the other side. So we can see that this equation is going to define a rule. So we want to make sure that we can really get y by itself here. Okay, so we can express this rule in function notation, and we'll see that in just a second. So we are going to try to get y by itself here. We'll add x squared to both sides. So that's y is equal to x squared plus 2. Yes, I can write this as a function of x. So I can say that f of x is equal to x squared plus 2. Okay. In the next one, when I solve for y, I would subtract x squared first. And then I would have to take the square root, and actually this might be a little less messy if I do the 4 first. It doesn't really make a difference. I would have to square root, so that's going to give me y is equal to plus or minus the square root of 4 minus x squared. The problem is this is producing two different equations. I'm getting positive square root of x, or square root of 4 minus x squared, and I'm getting negative square root of 4 minus x squared. So this is not defining y as a function of x. And that's really because it's producing two different equations. Okay. The graph of the, of the equations in this last example, in example 7, really are shown below. So if I were to graph A and B, I have a parabola in A as we see x squared plus 2. We have a circle with a radius of 2 in B, and when I take a look at that, even using the vertical line test, I can see that I don't pass that function test.